my goal with this chapter is I wanted to test next Wednesday and Thursday. Now, I know some of you said that you're going to be out, things are going to be going on. Hang on one second. But, no, not right now. We're going to be out on Friday. It has to be done, no matter who you are, what your situation is. If it's not done by Thursday, you get a 0 or you have whatever is graded by that Thursday afternoon. If one of the parts of the test is not done, I just got it out of my mouth. We're testing on Thursday, on Thermo Wednesday and Thursday of next week. Okay? You have to have it done by Thursday at 3:15 before I leave. Okay? The Thermo test. Next week, Wednesday and Thursday, we'll do the free response first. We'll do the multiple choice on Thursday. If you're going to be out or something, you've got to have that part taken care of. Now, so to finish this chapter up, some of this stuff will kind of go a little bit fast. Yes, ma'am. That's the second question I need to ask. Let me pause the video too. All right, so now you've seen this formula before, but today we're going to really dive in deep. Okay, guys, I really need you to pay attention because this is going to be very crucial for your understanding of this entire chapter. Now, I've already given you the acronym of the Ghetto Homies Take Speed. That's just a kind of funny way to remember this formula. But what you've got to remember is this is going to take delta H, we've talked a lot about. It's going to take delta S, which we have taught a lot about, and it's going to put them together in a way to make delta G more understandable. Okay, so we've got to be able to figure out how this works. Now, Peyton, can you read me that first sentence up there, please? Jacob, can you tell me? Can just please hang on? Come on now, like. All right, Brianna, go ahead, please. Thank you. All right, pause right there. So delta G naught equals 0. In that case, if delta G is 0, what is E? E is also 0 because E is also 0 because what is E? E naught. Cell potential. What is cell potential a measurement of? Voltage. What is voltage? Sir. Joules per coulomb. What is a joule? Energy. What is a coulomb? The charge of electron, the amount of charge of electron. So we have energy flowing. So without energy, can you do work? No. What is delta G? No. What is delta G? Free energy. So without power, can you do work? No. E is the power, G is the work. So if you have no work being done, what does that also tell you? You have no power. You have no energy. Okay, so that's what's going on here. Which means, not only if delta G naught is equal to 0, you just told me E was equal to 0, but what point in conditions are we? At equilibrium. Okay, Peyton, you want to keep reading that? In the red.
Which means the reaction is at equilibrium. Into consideration.
I don't know why that's there.
The equation rearranges rather quickly to allow you to determine the absolute temperature at which a process becomes thermodynamically stable.
That statement right there in blue is the most important thing we're fixing to talk about over the next 10 to 15 minutes. To determine the absolute temperature at which a process becomes thermodynamically favorable. So there's those three things that we keep talking about in terms of thermodynamics. If we want something thermodynamically favorable, what does G have to become? It's got to become negative. And that's what we're looking for. At what temperature does the reaction become thermodynamically favorable? So let me ask you something. I've just showed you this entire equation. Ghetto homies take speed. So why did G turn into 0 for this particular example? We're at equilibrium. And when you're at equilibrium, what is G? 0. So if you get rid of the 0 and you rearrange this equation, did you not exactly see this equation earlier? You kept seeing delta S equals delta H over T. You also saw the triangle where delta S, delta H, and T. But what part did they just solve for in the triangle? They solved for T. So T is equal to what? Delta H over delta S. So, what are H and S? Enthalpy divided by entropy. And so when we're trying to determine the temperature at which something becomes spontaneous or not, we need to know those two values. Because what's temperature dependent? Every freaking thing on the planet is temperature dependent. Okay? So that's what's going to drive all of this. Now, one other thing about when delta G is 0, again, what's happening when delta G is 0? It's at equilibrium. I need you to add this to that statement. When delta G is 0 at equilibrium, also what can occur? This thing right here. Phase changes can occur. And what the heck is a phase change? Okay, so we're going from one state of matter to another state of matter. Now, some of them are spontaneous. Some of them are non-spontaneous. Some of them are endothermic. Some of them are exothermic. But bottom line, regardless of what your delta H is, bottom line, regardless of what your delta S is, what is delta G at a phase change? 0. Why? Because you are at equilibrium. So when you read this, anytime you're at a phase change, this is equilibrium. Therefore, delta G is 0. And if I want to do this real quick, you've seen this graph, and it's not the one you're probably thinking of. Okay? You tell me, what is this graph representing? Change of states of matter. So we have temperature, and we have energy. Cody, where is a solid on this graph? Is it at the lowest temperature and lowest energy, or highest temperature and highest energy? Very good. So this is our solid region. Now, what is in this middle slant? Anybody? Liquid, and this up here is gases. And you already know that because what do gases have in terms of energy and temperature as compared to liquids and solids? More energy at higher temperatures. Is that true? Okay. Now, so the question that I'm proposing is what is occurring in these regions? Very good. So these are our phase changes. So our delta T is not changing, right? But is our energy changing? Yes. Okay. Technically, if we were moving from left to right, in this region right there, what's occurring? In the purple X, what's occurring moving left to right? What specifically? Which is melting. Very good. What's occurring in the green X? Moving right to left. Right to left. Which is? Gas to liquid, which is? Condensation. I just want to make sure everybody's on the same page with this. So there's two things that we can talk about. You told me here that this is solid to a liquid. So let's talk about delta S for a second. Now, what is S? Entropy. Now, what does entropy mean? Disorder. Is that becoming more ordered or more disordered? More disorder. So what's the sign of S? Positive. My second question. If this were, is this endo or is this exo? Closer together, farther apart. Farther apart. Energy in or energy out? If I want to separate something, energy has to go in. So this is endothermic. What's the sign of H then? Positive. So you've got a positive H and a positive S. Which one of those is what nature doesn't want? Why positive H? What does nature prefer? What does it like? It likes exothermic reactions. So you see what's going on? So in the terms of melting, you've got two things going on there. Okay? If I set an ice cube in a freezer, is it going to melt? But if I set an ice cube out here on my desk, will it melt? Why? What's the key factor? Temperature. So that's where all this is going. So let me ask you one more time. Up here, you told me we're going from a gas to a liquid. So my question now is, closer together, farther apart? Closer together. Endo or exo? Exo. Why? When bonds are made, energy is released. Now, let me ask this, and I really said that bad. Is that bonds being formed? No, that's intermolecular forces being formed. Now, is that becoming more ordered or more disordered? More ordered. So what is that? That's negative delta S. So we've got a negative delta H and a negative delta S. Now which one is going against nature's desires? Delta S, because what does nature prefer? Positive delta S. So do you see some differences going on? One of them is always going to be what nature wants, but the other one is going against what nature wants. So how in the world do these things happen? What's the major thing it's all dependent on? Temperature. Because there is a temperature at which it does not matter what nature wants anymore. Nature will force itself to do that. Because what is temperature also equivalent to? No. Energy. And if you have enough energy, you can do anything. If I gave you enough energy, you could run through that brick wall. Okay? You can make things happen if you have enough energy. All right, so we've got all these things. So anytime a sample compound changes from one type of matter to the other, so examples of phase changes. So freezing, evaporation, boiling, sublimation, melting, condensation, all those different things. I can ask you this. Do I really want to spend time doing this? Let's do one of them. Let's do the very last one. I don't feel like bending over, so I'm going to write it up here. Sublimation. Who can I pick on? Chris, what is sublimation? All right, so we're going from a solid to a gas. So Chris, tell me this. Are those particles getting closer together or farther apart? Farther apart. So is that endothermic or exothermic? If I want to rip your arm off of your body, tell me what I got to do with some energy. I got to put a lot of energy in, right? So that's endothermic. So what sign of H would that be? Positive, okay? Carly. Let's see, we talked about... All right, is solid to gas becoming more ordered or more disordered? Disordered. So is that positive S or negative S? Positive. Is that what nature likes or hates? Likes. Right. So again, we've got two different things kind of going there. So it's important that you understand those because these questions that we're fixing... Wow, I didn't even have to change that or draw it. I could have just looked at that. Yes, sir. Yes, sir. Yes, sir. Yes, sir. You are, but where's that energy coming from? From the energy that you've used to burn and to separate all those glucose molecules, right? Cellular respiration. Yes. Yes. So it is absorbed in him. That's why energy transfer is equal but opposite. I'm burning it, but he's gaining it. It just happens that his arm is going to be detached from his body at that point. Okay? All right, so the results from the calculations of delta S of the universe and delta G for a process of. Now, let's look at what's going on here. What is happening in that blue reaction? Solid to a liquid. Closer together, farther apart? Farther apart. Endothermic or exothermic? Endothermic. Okay? So if it's endothermic, what's the sign of our delta H? Delta H is going to be positive. Okay? Closer together, farther apart. You've already told me farther. So is that more order or more disorder? More disorder. So what is that going to be? Delta S is going to be positive. So again, who up here is going against nature? Delta H is. All right. So we've got water going from a solid to a liquid. One's at negative 10 degrees Celsius. One's at 0 degrees Celsius. And one's at 10 degrees Celsius. Now my first question is, what is the name of the process occurring here? In the blue. What's the name of the process? Melting. At what temperature does water melt? Very good. So, we know that this is the temperature at which water melts. So tell me something. What would you expect to see with your eyeballs at negative 10? But would you expect would you expect the process to occur at negative 10? No, why not? The amount of energy supplied by what variable? Temperature does not surpass the amount needed to boil. Excuse me, not to boil, to melt. All right, what would you expect to see at 10 degrees Celsius? It would do it quicker. Because why? What's happening when you go from 0 to 10 degrees? More energy, so things are going to happen a little bit quicker. You may. There's under that stack of stuff. So, at negative 10 degrees Celsius, Water has not begun to melt, so why is delta G positive? Yeah, because it's still non-spontaneous. So let's look at this. And the first row, so the temperature is 263, delta H is here, delta S is here. I'm trying to figure out the best thing. This is going to be a very important thing. And so when we solve for delta G equals delta H minus T delta S, that's the number we get. So we're still positive. So has there been enough energy put in yet to make it melt? No. So we're still not there here. And here's something very odd and strange. Look at that middle row. What is the value of delta G in that middle row? 0. So is it spontaneous or non-spontaneous? It's neither. It's what? At equilibrium. What's happening when delta G is at 0? It's that PC thing. It's a phase change. And you just told me 2 minutes ago, at this slide right here, that a phase change is at equilibrium and delta G is 0. So, technically speaking, does water really melt at 0 degrees Celsius? It's at 1. Does it? Not, yeah, does it melt? Does it begin changing phases? Does ice melt? Is that better? No, technically it's still water. So, again, here's why. So why is at 0 degrees Celsius the water, the water, is going through a phase change? So why is delta G 0? So I want you to write in. What's the answer to that? It's at equilibrium. Okay. So, in a weird, strange, odd little way, which one do you have more of? Do you have more solid water or ice? Or do you have more liquid water or water? Neither. It's at equilibrium. You with me? That's fine. It's going through the process of changing phases. It's not completely... Exactly. So, at 10 degrees Celsius, the water is completely in the liquid phase. So why is the delta G negative? Because nature is happy because it's gotten exactly what it wants. It has enough energy. But what was the only thing that changed this entire process? Thank you. And so what's the key factor in all of delta G? Temperature. Very good. So we can kind of move on to the this part right here. So I need you, and this is a tough question. If you can do this, I'm going to pass some stuff out while you do this. This is going to take a little bit. I need you to calculate delta G. But here's the problem. Look at what format they gave you delta H in and delta S in. So do I want to give you a hint or not? What do you have to do? That's number 1, but that's not the big thing. You've got to do Hess's law for H and S and then calculate G. Now let me tell you how this question is going to work in a real question setting on an AP exam. This would be one question, but it would be like 5 parts. So I'm just building a single question into one, but it would really be 5 specific parts because they'll give you this data, and like question 1 would be something random that you could easily answer. Like, what type of reaction is this or something like that. But the second question may be calculate the value of delta H. Question B would be calculate the value of delta S. Part C would be calculate the value of delta G. But guess what they're not going to give you in that question? They're not going to give you Hess's law, and they're not going to give you Getterholm's take speed. So you would have to know that when it says calculate delta H, what do you do with all these numbers? You have to put them in Hess's law. Okay? And the fourth part of this question would possibly be 3 ways. 1, is this reaction thermodynamically favorable or not? And explain why. Or, what is the sign of E? Or, what is the value of K in relation to 1? We could ask any type of those questions all based on this one set of data. So as you guys are doing this, I'm going to kind of be bringing some stuff around. So 2 things. Use Hess's law for H and S. Then calculate G. And I'm going to say this one more time in case you missed it because Devin said it. Devin, what did you say about the important thing that people miss? Kilojoules to joules. That is going to be the kicker that people are going to mess up, is they're going to forget to convert. Now, again, if it were me, I would convert the kilojoules into joules. Okay, so see if you can do this problem.